sides of the world, from the East and West. We are really glad and excited to have Becca Willett from University of Chicago. She's a professor there of statistics and computer science. Her research is focused on machine learning, signal processing, and large-scale data science. She received the National Science Foundation Career Award in 2007. She is a member of the DARPA Computer Science Study Group and received different and various awards. And today she will talk about machine learning and inverse problems in imaging. So welcome, Becca, and I will give you the stage.
Great, thank you very much. It's absolutely my pleasure to be a part of this seminar series. You guys have had a number of really exciting and interesting talks so far, and it's an honor to be a part of that. So what I'd like to tell you about today is some recent work that we've been doing in my group on trying to leverage machine learning to better solve inverse problems in imaging. And this is joint work with my student, Davis Gilton, who's going to graduate in about a week, and my former postdoc, Greg Ongi, who's now a professor at Marquette University. So like I said, we've been exploring inverse problems in imaging. And we think of it like this. We have some image that I'm going to call X that we're ultimately interested in recovering, but we don't have, simple pixel by pixel images of X like you would have with your smartphone, but rather you have some kind of indirect measurements, linear projections that may be corrupted by noise. So for example, there might be some pixels in your sensors that are dead, so you only observe a subset of the pixels in the image, or your image might be blurred. It might be lower resolution than you want, or in settings like medical imaging, such as MRI, you might observe case space or Fourier transform measurements, a limited subset of the Fourier transform coefficients of your image. So all of these diverse problems can be cast in the same way, where we take an image X and we multiply it by some operator A that represents what we call the forward model. And it represents, for instance, the blur process or the downsampling process, where it tells us which Fourier coefficients are observed. And then that's added to some noise, and that gives us our data Y. And our goal is to recover X from these measurements Y. So this is a problem that's been around for many, many years. And just to give you a sense of some of the challenges and techniques that were classically proposed, we could consider this example of deblurring. So because I wrote things with this nice linear form on the previous slide, you could imagine just trying to find the least squares fit. And that has a nice closed form expression here. That's a function of our forward model A and of our observation Y. And if I actually do a little bit of algebra, what we can see is that the estimate X hat then is the true image X plus our noise after it's gone through this operator that depends on our forward model A. So if there's no noise whatsoever, if epsilon here is 0, then we're going to exactly recover our image using this least squares solution. But if we were to take this blurry image and add even a tiny bit of noise that's even imperceptible to the human eye, and then try this least squares solution, we get complete garbage results. And what's happening here is that in many such situations, this forward model A is ill-conditioned. So it's got some small singular values, and ultimately this matrix that we have to invert has some really small eigenvalues. And so we can take even a tiny bit of noise in epsilon and multiply it by some giant numbers in this operator so that this corrupted noise here just drowns out the true image X. And so all the way back in the 1940s, we had methods like Tekanov regularization, where the idea is to say, instead of just finding the least squares solution, let's try to find a solution or an image X that's a good fit to the data in terms of squared error, but also where none of the pixels are too giant. And so this prevents us from having these sort of strange pixel blowups that kind of drown out any signal. And again, there's a nice closed form expression for this. And what we can see is happening is that instead of inverting a matrix that might have super tiny eigenvalues, we suddenly are making sure none of the eigenvalues are too small, and so we never blow up the noise the same way. And of course, this works quite well. We can see that, we still have some ringing, it's imperfect, but by doing this Tekanov regularization, we're able to do significantly better than least squares. So regularization is a general concept, and we've, in the intervening years and decades, looked at alternatives to this Tekanov regularization, where we just have this penalty or regularization term that corresponds to the sum of the squares of all the pixels. So for instance, people have looked at total variation, where they would define a regularization function that measures the sums of the absolute values of all of the, say, vertical neighboring pixel differences and horizontal neighboring pixel differences. Alternative methods have looked at wavelet sparsity and trying to build geometric models of images that say most of the wavelet coefficients of the images we want to recover are going to be 0 or very close to 0, and using that to construct a regularization function. And yet still other methods have said, if we were to take an image and split it up into patches, then a lot of times there's a lot of redundancy or structure among those patches, and we can exploit that to build alternative regularization functions. So in all of these approaches, we start off by thinking about some sort of geometric interpretation of the structure and the content of images, and use that to build a mathematical model that we can use to form a regularizer. And another way of thinking about this is that we are constructing priors. We're thinking about some sort of prior probability model about the distribution of images. And so when we talk about constructing regularizers, we're thinking about what the prior probability distribution is over images. So what I want to talk about today is a slightly different take on things, where instead of choosing this regularizer a priori based on some kind of smoothness model or geometric model, instead we want to learn the regularizer from a collection of training data. So this is something that in these broad strokes has been considered by a number of different people over the years, and I'll show you some examples later, but down here at the bottom, I even have a couple of recent reviews cited that kind of go over some of the broad categories of approaches. But the general setup, what we're considering is this. So we're going to imagine that we collect or synthesize a bunch of different training pairs, XY pairs, where for each pair, the YI corresponds to the XI through this forward model A plus some noise. And then we're going to train, for instance, a neural network on this training data that's somehow going to map Y to X. So it's going to take our observations and produce an image estimate. And so then at test time, we can take a new set of measurements Y, feed it into this neural network and get an estimate. So this is what we're going after. Here's an example with MRI, where we've got some observed case space measurements. We feed it into a network and get a nice reconstructed image out at the end, hopefully. So within this context, what I'd like to do today is to explore 3 key trade-offs that arise when we're thinking about how to design different methods and optimize performance. And the first one that I'd like to discuss is a trade-off between generality and sample complexity. So in particular, what I'm going to show is that when we know what this forward model A is, and we use that knowledge during training, then we can actually get better performance with fewer samples. But it's not very general in the sense that every time we've got a new forward model A, we might have to do some retraining. So let me explain what I mean by that. So to start, let's imagine that we actually knew a good regularization function. And we just want to think now about how we would solve this optimization problem, how we would find an image X hat that's a good fit to the data in terms of squared error and has a small value of the regularizer. So we might use, for instance, an algorithm like proximal gradient descent, where we start with some initial value and some step size, and we alternate between 2 steps. In the first step, we take our current estimate and we push it to be a better fit to the data Y. So it's basically a gradient descent step with respect to this squared error loss, or as we're going to refer to it today, a data consistency step. And then once we've done that, we can think of this intermediate estimate ZK here as being sort of like a noisy version of an image X that's not been regularized. It might be overly sensitive to noise. And so then what we're going to do is we're going to choose our next estimate of the image by essentially denoising that intermediate estimate ZK. And what I mean by that precisely is that we're going to try to find an image X that's close to Z, but which also has a small value for this regularization parameter. Okay, so in particular, that denoising step, as I had written it, has a special name. It's called a proximal operator, so we can write it in this slightly more concise form. And we can even represent this algorithm using a simple block diagram, where we take an input, image X, and we alternate between data consistency and a proximal operator. And we just kind of repeat this all the way until convergence. So when people first started thinking about trying to leverage machine learning here, one of the key ideas that emerged was to say, well, we know that this proximal operator is essentially doing a kind of denoising. And so what we might do is to train a neural network, for instance, a convolutional neural network, to denoise images. So learn a denoiser. And then what we could do is we could just plug in that denoiser into this proximal gradient algorithm. And so this has led to a number of different related approaches based on this kind of general concept. Earlier approaches were called plug and play methods. More recent methods have started from a slightly different standpoint, and they're called regularization by denoising. And yet more recent work has really focused on convergence guarantees associated with these methods and trying to understand what has to be true about the denoiser to ensure that these methods will converge. But ultimately, the idea is that once we've trained the denoiser, then we just take our initial estimate and alternate between this data consistency step and this neural network denoising system. Okay, so let's just think about or look at a little anecdotal example of this in action. So in this example, I've got the original image X and the observed Y, where there's a bunch of missing pixels that I want to be able to fill in. And if I were to train a denoiser using 80,000 training samples, then we see that we do reasonably well, right? We are able to figure out that we need to fill in a nose and an eye here. But if I were to crank down the number of training samples, say to 2,000, then all of a sudden the method performs quite poorly. And in fact, these methods generally require large numbers of training samples in order to perform well. And in applications like medical imaging, for instance, we don't always have such huge numbers of training samples, and we want to get as much as we can out of the training samples that are available. So why is it that this method, that this approach might require so much training data? So we talked before about how one of the ways that you could interpret learning a regularizer is that you're essentially learning some sort of prior probability distribution over the space of images. And once we know that prior, we can use that prior to, say, fill in the missing pixels. But arguably, this is overkill. Arguably, learning this full prior density is more than we really need to do with our limited amount of training data. So in particular, if we learn a full prior, we're having to learn about a lot of different pixels and geometric structure in this image that might be totally irrelevant to the in-painting task at hand. So in particular, if I want to be able to fill in the center region of people's faces, I don't really need to learn a model for background structure. Rather, I would argue that what we really need is to learn a conditional density estimate. What we really ultimately need to solve this inverse problem at hand is the distribution of all the parts of the image that are in the null space of A, conditioned on all the parts of the image that we observed. Or in the context of in-painting, we want to know what's the distribution of the missing pixels conditioned on the observed pixels. And it turns out from a wealth of statistical literature that conditional density estimation can actually require many fewer samples than estimating the full density P of X. So obviously we could estimate the full density and from that calculate the conditional density. But if the conditional density is smoother or if it is lower dimensional in some sense, then we can actually get very accurate estimates of the conditional density, even when we can't get good estimates of the full density. And so I think what we can conclude from this is that if A is known a priori, really we should be using it fully during the training. So with what we talked about before with these plug and play methods, we learned a denoising network that I illustrated here. But when we learned how to denoise, we didn't take into account at all the forward model A associated with the inverse problem that we were considering. Okay, so then we can say, all right, well, if we really want to use A during the training process, how might we do that? And it turns out it's just a minor modification of ideas that we've already talked about. So the first half of the slide, in fact, is already things that we've seen. Nothing's really changed here. The key difference is that when we talk about this class of methods that I'm referring to is referred to as deep unrolling. And when we talk about those methods, the idea is that we start with some sort of iterative optimization scheme. But instead of learning our denoiser offline, plugging it in, and then iterating until convergence. Instead, what we do is we say ahead of time, we're only going to run for capital K iterations, or capital K blocks in this block diagram. And then what we do is we try to train the weights of this neural network so that the output after K blocks is as accurate as possible with respect to our training data. So instead of training the neural network offline and ignoring the forward model or the inverse problem at hand, instead, we're optimizing these weights in the context of this big giant network or big giant system that incorporates knowledge of the forward model A through these data consistency blocks. And we're going to see examples of this in action. And in general, this provides more accuracy with fewer samples than the plug and play approaches for a variety of different inverse problems. So Yonina Eldar and her team recently wrote a review article of deep unrolling, and they cited a number of different approaches that have explored this. So we've only talked about it in the context of proximal gradient, but it's been explored from the perspective of many different kinds of optimization standpoints, but also many different kinds of applications. Okay, and so what the main point that I've been trying to convey here is that when we take methods that are trained for a specific forward model A, then in many cases they can outperform what I would call model agnostic training. So pre-training a network without taking into account the forward model A in the setting where data is limited. But of course, the caveat to that is that it must be retrained for each new forward model A. So here's just some numerical results to support this claim in the context of deblurring, compressed sensing, and MRI reconstruction. And what we're comparing here is total variation reconstruction, where there's no learning at all. There's no real training data being used. Gold and red are what I would call model agnostic training, so plug and play or regularization by denoising. And then in green, we have an example of this unrolled proximal gradient approach. And for all of these applications across a number of different examples and test cases, the unrolled approach performs better. Okay, so this actually, I think, is a good point to pause and see if there are any questions. I feel like I've seen a couple of things pop up with Zoom, though it's a little hard to see. Were there any questions so far? Oh, okay, I can see it now. So it looks like Fernando says, if we were to sample from these priors defined by the regularizer, assuming that it's possible, should we get plausible images? So if you had a true prior that really did correspond to how images were generated, then yeah, you should be able to get plausible images from them. I would say, though, in practice, that it doesn't quite work that easily, right? Often these priors are either chosen to have nice mathematical properties so that we actually can find good solutions to the inverse problem, either through some sort of Bayesian approach or through some sort of optimization approach. And in which case, since they've been chosen with mathematical convenience in mind, it might be a little bit trickier to ensure that all the images sampled from it are really nice looking. And if you were to try to instead use something like, let's say, a generative model or a GAN to try to represent your prior, then in general, you need a whole lot of training images in order to get that prior to be accurate. So yes, in general, if you had a good prior, you should be able to draw from it and get good images, but getting a good prior is tricky in general. Tassin asks, do we assume we know A in these methods? What if A is parameterized on our signal and we don't know it explicitly? So great question. Yes, in everything that I'm talking about here today, we do assume that we know A. There are methods that try to solve these problems without knowledge of A. And certainly in areas like, for instance, de-blurring, they've been reasonably successful. But in problems like compressed sensing, I think they don't work nearly as well. So to some extent, it depends on what that forward model A is when you're trying to do learning. So you can think about it as if you don't know A and you just want to learn a reconstruction network, then essentially you need enough training data that you can not only learn the structure of images in X, but also learn what this operator A is doing. And that requires a whole lot more samples than if you have that knowledge of what A is. In terms of what happens if maybe there's some error in your estimate of A, that's something we're actually going to talk about. That's the third trade-off. And if we've got parametric models, there are some techniques that are out there, but I won't have time to talk about them today. Okay, so Gonzalo says deep unrolling of K blocks means that you train K neural networks end to end. So that's not quite what I meant, and I'm just going to actually go back to the slide to make sure that I make this point clear. So I've got these K different blocks, each one consisting of a data consistency term, so just a simple linear operator, and a neural network that's operating as a denoiser or something like a proximal operator. And so I've got K different neural networks in here. What I'm doing is I'm choosing their weights so that the final output of the whole system is as good as possible. So there's two different regimes that are common. One is called weight tying, where we force all of the neural networks in all of the different blocks to be equal. And then, of course, the other regime is where I don't force that. So if I force that, then I really only have one neural network that I'm learning, but it's appearing K different times in this diagram. So hopefully that answers your question. In our lab's empirical investigations, we've looked at what is the performance effect of weight tying. Like, does that make the results look a lot worse if we force us to only have one neural network that's the same in all of these blocks? And the answer is no. We seem to do about the same whether we do weight tying or not. Oh, and then Phil asked if I advocated using a different denoiser at each stage. And so, yeah, I think I just got that one inadvertently. Thanks, Phil. Of course, I mean, I want to be clear, like this is based on our team's empirical experience with a certain set of inverse problems, right? Deblurring, compressed sensing, MRI, super resolution, and in-painting. So I don't think I can make a general claim for all classes of inverse problems. But for the problems that we've looked at with the quantities of training data that we've had available, weight time doesn't seem to yield much of an advantage, and none in some cases. Okay, so yes.
Follow up on that. I think maybe there are other questions coming up, but so you're saying you're not tying the weights across the denoisers, right?
Oh, I'm sorry. I'm saying that in the community, some people do and some people don't. In all of the experiments that we're considering here, we are doing it. We are doing weight tying. One of the reasons for that is that this way we can kind of do a more apples to apples comparison with something like plug and play, where both methods have the exact same number of parameters. It's not like the deep unrolling has some advantage because it's got way more parameters than anything we're doing with plug and play. So yes, for all of the things in this presentation, we are doing weight tying. The denoiser or the neural network is the same in each of the different blocks.
I see. So I guess that would correspond to a more conventional, I mean, that would tie to a more conventional type of regularization where the regularizer is kind of fixed and maybe it's like a, you know, sparsity L1 penalty, and then you're doing just the same thing each time, some sort of thresholding. And so you're, but it's still, I think it's still unclear how that would compare to having the network change. And that kind of reminds me of, you know, things like, you know, dictionary learning where the dictionary is adapted over the iterations. There the regularizer is in fact changing. And as, you know, the image gets cleaner, you get something different. And maybe the regularizer adapts to the image being cleaner and it denoises more appropriately then. So have you done a comparison between these two approaches, or do you have, you know, further thoughts?
Right. So like I said, we've done some empirical comparisons in my group, and we have seen no statistically significant difference between weight tying and no weight tying. And in fact, the kind of next block of my talk, I'm going to that's going to be an important point. So it doesn't really seem to give us an advantage. I can't really make a broader claim, though. It's not like I can say you're never going to find an inverse problem and a quantity of training data where weight tying gives no advantage or gives an advantage, right? So I think on a foundational level, we don't totally understand this. And I think, you know, your suggestion of trying to understand it through the lens of some past work on adaptive dictionary learning is a really interesting idea. But yeah, I haven't really seen a careful comparison on a foundational level or even on an empirical level in many of the papers that I've read. And yeah, I just think it's not a well understood phenomenon.
Mm-hmm. Okay, thanks, Becca.
So Ali says, you know, most previous methods such as compressed sensing are general. And I think by that, Ali, maybe you mean like sparsity regularization. And so he says, okay, if you train your deep learning models on a type of MRI images, you get better results only on that type of data. What's your idea on the generalization of learned models to more different scenarios? Yeah, that's a great question. So if I was going to learn how to reconstruct MRI images, I probably would not train on celeb A data, right? Because I just don't expect my MRI images to look like pictures of celebrities. And so again, I think a good way of thinking about this is that what we're really trying to learn is some sort of prior probability model or some kind of conditional probability model of what the image might look like given the measurements. And so, you know, just like, you know, when we were using geometric models to build regularizers, we thought, well, what can we say about the geometry of MRI images, such as sparsity and a wavelet basis, in order to construct a good regularizer? Here, we're going to say, how can I get training images that are really representative of the application of interest in order to form a good prior model? So Vivek asks, to what extent is retraining necessary or helpful when the data consistency term is changed? So I'm not exactly sure, Vivek, what you mean. If you mean it's changed because A changes, then super important. And if we have time, I'll talk about that a little bit today. If instead you mean, well, we formed this data consistency term based on, say, a squared error measure of fit. And so if I wanted something else, like Poisson negative log likelihood or something, then do I need to kind of change my regularizer? I'm not sure. I think we really don't understand a whole lot about the right way to handle these things when you've got different kinds of noise models or different kinds of data fit measures. I think that's pretty wide open at this point. Okay, these are all such great questions, and I'm super happy that you guys are all so engaged. So Sundaresh says, we mentioned image super resolution and deblurring, but are we really super resolving the images with such an approach? Oops, it moved. Are we really super resolving the images with this approach, or are we just enhancing them to make it look good and appear better to the eyes? Yeah, this is a great question. There have been some kind of discussions about what is really happening when we do super resolution reconstruction, and certainly it's not super resolution the way a physicist would refer to it. And I think it is more akin to in-painting in the sense that we're kind of filling in missing data based on our prior knowledge. Sundaresh also keeps moving on me, sorry. Sundaresh also asks, in something like MRI, will we be able to capture defects or disease conditions that don't show up when we capture information in the K-space? So in our focus, and most of the community's focus so far has been on measures like PSNR or on SSIM's structural similarity image measure or something like that. And so, of course, you're right, that does not capture something like, whether a doctor is going to be able to make a good diagnosis from it. And I think there's a real need to think about whether we can integrate techniques for, trying to identify tumors or lesions in images with these reconstruction methods. That's certainly a nice possibility. And then there's other kinds of techniques that we can use when building these denoisers or networks that ensure that they're a little bit more localized, that can also help with the detection of unusual features like tumors. Okay, David Morales asks an awesome question that I'm going to not answer because it's the next part of my talk. So I'll come back to that one. And so Saeed says, yes, do we need to decide on what regularizer to use? Yes, that's exactly right. That's what we're trying to do with the denoising, is figure out what regularizer to use. What's the relationship between deep unrolling and the conditional probability mentioned just before? All right, so Dirk, that's a great question. We've got some earlier work that actually explores this question in the context where all of the images X lie in a union of subspaces. And we're able to kind of show that we're capturing essentially the structure of that union of subspaces. So we are, but in a way that's somehow dependent on the forward model at hand. I don't have slides to really support that, but it is something that we looked at in our paper on Neumann networks that you might find interesting. Daniel asks, if one knows A, where is the model of A obtained? So generally that would be, I would think of that as being part of, calibrating your sensor. So for instance, if you've got an MRI scanner, then the choice of A is dictated by all the different knobs and choices that you have for how you set up the scanner. But also when they build the scanner, they actually calibrate it very carefully so that they can get a good estimate of A. And the same is true for computed tomography. With satellites, they do all kinds of calibration experiments. And so there's a number of different techniques for estimating what A is. But yeah, it is just a function of the electronics or the sensor. So Yuhao asks, does every block improve the recovered image quality a little, or will some blocks degrade quality? I would say on average, yes. If you were to look at the output at successive blocks, they generally get improved with each block. And then there's another question, what about the regularization parameter? And I think that's a reference to this step size eta here. And that we treat as a parameter also to be learned with all the other parameters, or with all the network parameters that we're also learning. Great. Well, thank you guys so much for the awesome questions. So let me just mark these as answered because I want to be able to not be redundant. So like I said, well, we just talked about how we might or might not leverage knowledge of A during training. So the next thing I want to talk about are convergence properties, which was a question that I think David Morales asked, which is excellent. And in fact, here's a picture kind of illustrating something about convergence. So with this deep unrolling method, let's say that we train it to be doing good after 10 different blocks. And 10 is a pretty standard number in these systems. So then you might say, well, once I've trained it for 10 blocks, at test time or at deployment, I could actually just keep on running it. So I could say, well, I've learned a network. I'm going to treat that network as sort of a denoiser, and then I can run as many iterations as I want. So here's the result at test time of iterating after 20 iterations, after 30, 40, 50, etc. And we can see, even after just 50 iterations, that we start getting some pretty significant artifacts, and they're gradually worsening. And in fact, this does not converge. It diverges, and it diverges into something that nobody would want to see on their knee. And in fact, we can kind of look at this a little bit more systematically. So what I'm showing in this plot are curves corresponding to this unrolled method with proximal gradient, where it's trained to do well for 2 blocks, or 6 blocks, or 10 blocks, or 14 blocks. And then what we're doing is at test time or at deployment, we're going to run it for the number of blocks or iterations on the horizontal axis here. So if we focus on the orange curve for a moment, we trained it to do well after 6 blocks. It does do well after 6 blocks with a PSNR of about 29. But if we keep running after that, then it gets worse. If we were to train for 10 blocks, then it does best at 10 blocks, but anymore, the performance degrades. And you might say, well, can I do better by just increasing the number of blocks? But you can see that even with 14 blocks, the peak performance at iteration 14 is just not as good. Now we've slipped below 28 PSNR. And so you might ask, well, what can we do here? Like, these methods are not converging, and it's not like just adding on additional blocks is going to get me better performance and better convergence properties. And so this is where some of our recent work on deep equilibrium models comes into play. So what we've seen so far is this plug and play kind of category of methods, which do have some nice convergence guarantees, but empirically don't perform quite as well as deep unrolling, at least when we've got limited quantities of training data. And in contrast, deep unrolling methods, where there's no convergence guarantees, and not only no guarantees, but it really can diverge if we run this for more iterations, but generally gives us state-of-the-art results. And so with these deep equilibrium approaches that I'm about to describe, we're going to be able to get both convergence guarantees and state-of-the-art performance. So here's the basic idea. If we were to take some sort of method and run it to convergence, then we can think about the final estimate at convergence as being the fixed point of some nonlinear function f. So for instance, with proximal gradient descent, we had a bunch of different blocks where with each block, we did a data consistency step and a proximal operator. So in this context, we can think about f as being the composition of those two things, right? My data consistency step here, and then my proximal operator. And so if we were to iterate this until convergence, then our final estimate would be a fixed point of that function. And we can kind of say the same thing if we were to, instead of having a formal proximal operator, have, for instance, a neural network here. It still defines some sort of function, and the output at convergence would be a fixed point of that function. So our strategy is then going to be to try to learn neural networks so that the corresponding fixed point is good. So if I refer to theta, if I let theta correspond to all the weights in my neural network, what I want to do is I want to learn theta that's going to define a function f sub theta. And we want to ensure that the fixed point of this function gives us a good reconstruction of the image. So for a long time, this sounded totally reasonable, but it wasn't really clear how we would actually solve the optimization or the training problem, how we would actually choose the thetas to ensure that the fixed point was good. But some recent work on deep equilibrium models actually showed how to perform back propagation on estimators that were defined through pretty generic fixed point equations. And so we're able to kind of leverage some of those techniques in order to come up with a way of learning good fixed points for image reconstruction. Because of the questions and we're running short of time, I'm going to gloss over some of the details here and just kind of hit some of the highlights. So basically, we've got a method for actually learning these parameters theta, giving us a good fixed point without actually having to have an infinite number of iterations. So it's all implicit. We can show that if this map, this fixed point equation that we learn is contractive, then the iterates will converge to a fixed point and it'll convert and it'll be linear. In addition, if we ensure that our denoising network has a bounded Lipschitz constant, then it ensures that this map is contractive, so we get convergence. And empirically, we can use techniques like spectral normalization in order to ensure that these Lipschitz constants are bounded. Okay, so here's this in action. Here's the ground truth image we want to reconstruct. This is what happens if we fill in all the unmeasured Fourier coefficients with zeros and then do the inverse Fourier transform. This is a result of deep unrolling and deep equilibrium. And I'm going to focus in on this little cyan block here and show how there are certain regions in the knee that are diagnostically significant that are distorted by the deep unrolling methods and accurately recovered by these deep equilibrium approaches. In addition, once we've learned this map, this f sub theta, then at deployment time, we can run as many iterations as we want, and then we actually kind of converge to something good. So I think I see, no, sorry. So here's another view of the same information. So here we have, similar to before, the reconstruction accuracy as a function of how many iterations we use at deployment time. So what we saw before was essentially this green line, where we train to do well after 10 iterations, and we do well after 10 iterations, but we just can never beat that. We can't continue to iterate, because if we continue to iterate, everything falls apart. In orange, we've got these plug-and-play approaches where things do kind of stabilize in a nice way. They have convergence guarantees, but they never quite get up to the level of the deep unrolled method. And then finally, in blue, we've got the deep equilibrium approach, where we're able to do, in a small number of iterations, just as well as deep unrolling. But if we give ourselves the flexibility to continue to iterate, if we spend that extra time at deployment to iterate till convergence, we can get even higher accuracies, going all the way from 29 PSNR at 10 iterations to 31 PSNR after, let's say, 100 iterations. And this is a plot for MRI, but the same kind of phenomena occur if we look at deblurring and compressed sensing. And because in past talks these questions have come up, I want to emphasize that the amount of memory that's required in order to do this is 1/k, the amount of memory that deep unrolling needs with k blocks. The number of parameters that we have to learn, the size of this parameter vector theta, is the same for deep unrolling versus deep equilibrium. Training takes about twice as long, but it's not, a huge factor. And the inference time corresponds to the horizontal axis in these plots. And finally, we can return to this bar chart that I showed you earlier, where before we were only looking at the gray, gold, red, and green lines. And now I've added in the blue lines showing the deep equilibrium approach. And we can see that it's outperforming all the previous approaches, sometimes by a pretty sizable margin. Okay, so with that, I want to use just a few minutes to at least capture the highlights of this third trade-off that I think somebody even asked about in some of the Q&A between reconstruction accuracy and sensitivity to model mismatch. So I spent the first third of the talk making a claim that methods that were trained for a specific forward model A were able to outperform methods that did all of the kind of training offline before knowing anything about the inverse problem at hand. And that's true, but of course the key caveat is that if we were to train for one forward model, let's say A0, and then at deployment time have a new forward model, then things start to break down. So this is especially relevant in something like MRI, for instance, where in MRI, maybe you've got slightly different K-spaces or slightly different Fourier coefficients that you're measuring. Or maybe you've got a different undersampling factor or different coil, number of coils or coil sensitivities, etc. Okay, so remember that the main paradigm was this, right? We got a bunch of training data. They all come from one forward model. We're going to call that A0 now. And we're going to assume that we've got tools that allow us to train a reconstruction network so that we can feed data Y into the network and get an estimate X hat. And now let's see what happens when we try this out on MRI. So on the left is the ground truth. On the right, we've got pretty much what we've been talking about all along here, where the forward model is A0, and it's the same when we train as when we test. And we see it works really well. We've got almost 32 dB PSNR. But then finally, on the far right, what we're seeing is what happens if we train for one forward model, say one set of Fourier coefficient observations, but then at deployment or test time, we change what those Fourier coefficient locations are a little bit. And we see with that slight shift, we suddenly get a huge drop in PSNR, almost 5 dB. And we can also see some artifacts emerging. So things just really start to break down. And so the question is, well, what should we do about this? How can we not have this huge breakdown when there's a small shift in the forward model? And I'm sure many of you have already thought of some possible solutions. One would be to just retrain the network every time we say change our MRI scanner. But that's computational costly. And in addition, you might not really have the training data widely available so that anybody and everybody can train on it every time they make a little tweak. You might also say, well, let's train on an ensemble of forward models. So let me just train for every possible, say, K-space trajectory or every kind of sampling pattern in MRI. That's a little tricky because it's a pretty high dimensional set to sample from. And when we've done numerical experiments along these lines, it hurts performance a lot. This is worse than doing nothing. Another possibility is to say, hey, with plug and play methods, they're trained in a way that does not depend on the forward model. And so you shouldn't have to worry about model drift there. And that's totally true. But again, empirically, we find that we can outperform those methods, especially when there's a limited amount of training data, so we might not be able to learn the perfect regularizer or denoiser. And so the option that we're going to discuss here is an alternative where we try to adapt the network to solve the new inverse problem. Okay, so we're given some sort of network that has been trained to solve an inverse problem with forward model A0, and now we want to use it somehow to solve the inverse problem with forward model A1. And for now, we're going to assume that A1 and A0 are both known. And the key idea behind our approach is that we know that this network we trained for, when composed with A0, acts something like an autoencoder. So if I were to take an image and feed it through forward model A0, and then feed that product into F theta, hopefully I'm going to get out something that looks a lot like X. In fact, that's what we trained for. That's what F theta is designed to do. And so we're going to use this property in order to design a regularizer for our new forward model A1. So in particular, we're going to take the regularization by denoising framework, and we're going to use our old trained model as our regularizer or denoiser. So the cost function that we're essentially going to minimize corresponds to making sure we find an image that's a good fit to our data using our new forward model, but we're going to regularize it using our old forward model and our old trained network. And so what we can, if we actually look at what the iterates look like, then we actually have two steps. There's a data consistency step like before, and this depends on the on the new forward model A1. And then a regularization step that depends on the old forward model and our old neural network reconstruction method. And so if we look at this in action, what we can see is that the two forward models are just slight perturbations of one another. And you saw these middle two pictures before. This is what happens if, we actually had not shifted to A1. So this is, not the world we're living in, but the world we wish we were living in. And this is sort of the gold standard or the target quality we're hoping to achieve. If we fail to adapt to our new A1, then just like I said before, we get this 5 dB drop in artifacts and it performs poorly. And if we do model adaptation, as I've described to you, then we actually get a PSNR that's comparable to if we had trained from the right model in the first place, and which lacks the significant artifacts that we see without model adaptation. I want to show kind of the same idea again in a slightly different context that I think is especially remarkable. So in this context, we train for 6x acceleration. That means there's like 6x undersampling. But then at deployment, we collect more samples. We're only doing 4x, or we're doing 4x acceleration, or we have 4x undersampling. So this means we've got more samples, and the new inverse problem is even easier than what we trained for. And so in this slightly modified setting, what we see is that if we train on A0 and test on A1, we still get this huge drop in PSNR. So even though at test time, we're working on an easier problem than we trained for, we're still paying a price. Whereas by using model adaptation, we're able to actually get all the benefits of the easier inverse problem and do significantly better. So we're able to leverage all the additional data or all the additional samples that we acquire here. So let me just show you one last plot, and then I'll show you my concluding slides. In this plot, maybe I'll just highlight a couple of things. So the red curve corresponds to regularization by denoising, where we pre-train the network without knowing the forward model. And so here we don't have to worry at all about, whether we trained for one forward model and have to adapt to a new forward model, because we just learned a generic regularizer or a generic denoiser. And in contrast, in blue, we have our methods based on reusing the old network and as a regularizer. So we call it R and R. And so we can see that across the board, the blue is doing generally better than the red. That by using these model adaptation approaches, we're able to outperform even sort of these generic approaches and do almost as well as these gold bars, where the gold bars you can think of as a gold standard, where we actually trained for the correct forward model in the first place. So again, not the world we're living in, the world we wish we were living in. And so we're able to adapt so well that we're doing almost as well as if we had known the right forward model in the beginning. Okay, so with that, I just want to very quickly summarize these kind of three key trade-offs that we discussed today and point you to relevant papers that actually dive into some of these details about these trade-offs and methodologies that I presented. And I'll just leave this up here in case you want to copy down any numbers or anything, and I'd be happy to answer any additional questions. Sai.
Hi, Becca. Very interesting work, and I think we should catch up a little later. We've been working on a lot of similar things recently as well, and I'm very interested to maybe chat offline. But for now, I had a couple things. So the fixed point setup, I was wondering what is the optimization for learning the theta that you were doing. So what is like the problem that you were solving when you had the fixed point equation? And the reason I ask is we tried something like that recently, but our fixed point equation was different because our fixed point equation had an argmin of an loss function with different kinds of regularizers and a network in there. So that turned out being much more complicated when we tried to learn the theta, because then we had to do this sort of bi-level optimization. And
right.
that
so I've got a couple of things I can say about that. So first of all, just like with any of these things, we're going to try to learn theta by doing stochastic gradient descent. So we've got a loss, and we have to compute the gradient of the loss with respect to theta. And so we use the chain rule. So we say, what's the gradient of the loss with respect to the fixed point, and the gradient of the fixed point with respect to our parameter theta. And it's this second factor that's the tricky one. So what we do in order to think about this is we go back to the fact that we've got a fixed point, and we compute the gradient of both sides of this equation. So on the left, we've got the gradient of x star with respect to theta. And on the right, we've differentiated using this fixed point expression. And we can see on both sides, we get dx star d theta. And so then we combine like terms and we get this nice expression. And this turns out to be something that we can compute. Now, you mentioned something else where you've got somehow a fixed point that depends on an optimization problem. That sounds super interesting. I would say that Zico Coulter, who's one of the authors here, and maybe even some of his co-authors, they have another paper where they actually do also talk about figuring out how to backpropagate through a minimization problem that might be relevant to what you're doing. So I can pull up that reference and send it to you. And if you want to talk about it, I mean, I think their stuff was a little bit more generic, if I remember correctly, and not really specific to inverse problems in imaging. So it might be really fun to think about together.
Yeah. I think we should chat more about this. So your loss function is essentially just x star is f theta of x star. So that's you're enforcing your fixed point condition at the sort of the ground truth images, right? And sort of you're minimizing the fidelity. Is that the loss function?
Right. So for each training image at xi, it's got a corresponding yi. I'm going to, let's say my initial estimate is just A transpose Y, right? So I've got to have something of right size. So I'm going to now feed this into this system, and I want to find the fixed point of this equation. That's going to give me an xi hat, and I want the squared error between xi and xi hat to be as small as possible, averaged across the i's.
Mm-hmm.
So there's a couple of questions in the chat as well. I apologize if I mispronounce your names. I think Vaibhav. He asks, or she asks, can the problem of having different forward models be thought of as a domain adaptation problem? I would say yes and no, in the sense that, when I think of domain adaptation, I generally think of, let's just think about supervised learning. I've got XY pairs coming from one distribution at train time, and then I want to adapt to another distribution at say, test time or at a later point. And I don't know anything about that distribution drift, except that, I've got training samples before and after. And I think with what we're doing here, we call it model adaptation. And I think of it as being a little bit different for two reasons. One, we actually have a model for what that domain drift is, right? We know what's changing. The thing that's changing is the forward model. And there's a linear relationship between the X's and the Y's, and it's the nature of that linear relationship that's changing. So it's much more specific than what you often see in domain drift and domain adaptation. And at the same time, we assume that we've got something a little bit different in terms of what data we can use to adapt to this new domain. So I didn't detail it much in the slides, but we do consider two regimes. Let's see, where's the right slide? Not this one. So in one regime, which is the one I focused on, we don't really have any new data after the domain drift, except for our new test data Y. So with domain adaptation, you might assume that you've got a small number of training samples after the distribution drift. We're not assuming that. We're assuming that we just have our new test sample and some knowledge that there was a change in the forward model. We've done some additional stuff where we've got some limited calibration data, but even that's different than what you would normally assume in the domain adaptation setting. So great question. Like, there's some subtle differences, but I think it's closely related, but we're basically exploiting kind of the special nature of the type of domain adaptation that we have here, that have to deal with here. Denise asks a practical question. Well, we can make slides available. Yes, I would be happy to. I will coordinate with Sai on the best way to do that and get it out to everybody. Or yeah, any of the other hosts too. Sorry, I know Raja invited me here. I don't want to neglect him. In your experiments, what was the size of the matrix A? That's a good question. And it was different for compressed sensing versus MRI versus deblurring. And I apologize, I don't remember off the top of my head. I know that it's in the papers, though. I'm sorry, I can't be more concrete right now. Nargis says, what modification is applied to the network to enforce convergence to the fixed point when you're moving from deep unrolling to deep equilibrium approach? So basically, I mentioned it super briefly here. We use a previously published kind of normalization during training called spectral normalization. And so it's a little extra step that we take after each gradient descent step during the training process. And so by doing that, we can ensure that the Lipschitz constant is bounded, and therefore that the map is contractive, and therefore that we converge to a fixed point. Hassan says, can A0 and A1 be different enough that, for example, one operator is a subsampled Fourier matrix and the other is an undercomplete Gaussian matrix? Yeah, Hassan, this is a super question. I mean, I think I showed everybody this plot at the end. And the thing I highlighted is that we do better with model adaptation than these methods that are somehow like pre-trained for generic forward models. But we really focused on the setting where A0 and A1 are just slight perturbations, are not too giant of a difference between one another. And the reason for that is that basically the way I think of what we're doing whenever we train one of these models is that we are learning this conditional distribution. What's the distribution of the parts of the image in the null space of A0 given the stuff in the range of A0? And so if A1 now comes along and its null space has nothing to do with the null space of A0, if they're just totally different from one another, then whatever I've learned about reconstructing A0 may be useless for reconstructing A1. And so I think, the margin of difference between these approaches that I'm proposing, where we adapt to the new model, versus a method that's just trained for a generic forward model, is going to depend a lot on the amount of similarity between A0 and A1. At this point, I don't know how to measure that similarity, right? Like, I don't know mathematically how to characterize when this will work better and when it'll work worse. And so we've done some empirical experiments, but I don't really have a complete answer at this point. But it's a fantastic question and very interesting. Okay, so another question is, since we're using the mean squared error criterion, what impact do outliers have on the learning performance in your system? In particular, your proposed adaptation-based system. Right, so we really are assuming that all of our training data is IID from some distribution that corresponds to this sort of forward model that I specified before. So if you wanted to assume that we also had some kind of adversarial samples thrown in there, I think you'd have to develop some new techniques, and it would be interesting to see how some sorts of adversarial training might have an interplay with some of the techniques that I described here today. But it is a somewhat different problem space that we haven't really studied. Yeah, very interesting question. So Nicola says, how do you decide on the architecture of the Prox Op CNN? How are we limited by this choice? Yeah, I really wish I had better insights I could give you there. So within this general framework that I described, what we've used the most here is a UNet. I think my student has recently done some additional experiments with a different network architecture that seemed to be performing even better. And we're going to post that in the next week or so here. But I don't know that I have any like real helpful guidance or rules of thumb. So we've been looking a lot just at the computer vision literature and thinking about what kinds of architectures are useful for different tasks and trying to leverage those existing, learned representation models the best we can. It is interesting to kind of think about what kinds of influences different architecture choices have, but I don't think we understand that question in any setting, let alone in these inverse problem settings. And then Pi asks, what spectral normalization technique did we use? And we used the technique from the Miyato 2018 paper. Okay, I can see that I am grossly over time here, but I really appreciate all the questions and interest.
So thank you very much for the very interesting talk. And I thank all the audience for coming, and hope I'm sure everyone enjoyed this great talk. So thank you very much, and see you in 2 weeks.